We're going to do trig integrals that are combinations of tangent and secant. We can do this because 1 plus tangent squared, an angle, is secant squared. So we can express tangent squared in terms of secant squared and vice versa. So we know that secant squared is just 1 plus tangent squared, but we can say that tangent squared is just secant squared minus 1. We're going to look at the integral tangent to the nth power secant to the nth power dx. And we're going to do this in cases. Our first case is we're going to let m and n be both odd integers. As an example, we will do the integral of tangent cubed x secant cubed x dx. In looking at this, I'd like to have a choice for u. If I let u be secant x, then the derivative of u is secant x tangent x dx. That means I just have to pull 1 from the tangent cubed and 1 from the secant cubed. In doing this, I will have my secant x tangent x dx right there. And that leaves me pulling 1 from tangent with tangent squared and 1 from secant, secant squared. And that's going to work fine because I can replace a tangent squared or a secant squared. Working this out, I have tangent squared, secant squared, and then I've got my secant x tangent x dx. This is my du, and the secants are my u, so now I have to change tangent squared in terms of secant squared. I do that from the identity which says tangent squared is secant squared minus 1. This then becomes a u squared minus 1 here. I can now write the u substitution. The integral becomes u squared minus 1 times u squared, and then I have du. We just distribute this through, and that gives us u to the 4th minus u squared du. And now I'm ready to take antiderivative, which is u to the 5th over 5 minus u to the 3rd over 3 plus a constant. But replacing u with the x expression, it is just secant x. We've got that right here. So we write the answer as secant x to the 5th over 5 minus secant x to the 3rd over 3 plus a constant. And that becomes our answer. Our next case we are going to do, I'll call it case B, where m and n are both even exponents. So I'm going to go to the next page. Let's do as an example tangent squared x secant squared x dx. My choice for u in this one would be tangent, because then the secant squared dx is my du. This now becomes u squared du. So this is the integral of u squared du, which is u cubed over 3 plus a constant. And it works out nicely. This becomes tangent cubed x over 3 plus a constant. Now we'll go to another example. And our other case is where one exponent is odd and one is even. For this one, as an example, let's look at the integral of tangent cubed x secant to the 4th x dx. One way of thinking about this, because I have an even number of secant, that's a perfect choice for that to be my du, which means it came from u being tangent. Writing this out, I have tangent cubed x. I've pulled out a secant squared, so I have secant squared x, and then I've got the secant squared x dx. This is my du, this is my u cubed, and that means this secant squared has to become a tangent, and it does because it's 1 plus tangent squared. I now have this as 1 plus u squared. I'm now ready to write it as the u substitution it is. This becomes u cubed times 1 plus u squared, and then we've got du. We just distribute the u cubed through, and this becomes the integral of u cubed plus u to the 5th du. And now very straightforward antiderivative, u to the 4th over 4 plus u to the 6 over 6 plus a constant. So this is just tangent x to the 4th over 4 plus tangent x to the 6th over 6 plus a constant. Worked out very nicely. We're now ready for the example. This first one is we had secant was even, but now we're going to do one where tangent is even and secant is odd. The example I'd like us to do would be integral of tangent squared x secant cubed x dx. This one I can't let u be tangent because when I take out a secant squared I only have one secant. I can't replace it easily. If I take out tangent secant as du, I have only one tangent. So this is going to involve integration by parts. We're going to have to do by parts. But before we do by parts, we are going to use an identity. We're going to change tangent squared to secant squared minus 1. Doing this, this becomes the integral of secant to the 5th x minus secant to the 3rd x dx. I'm going to do both of these separately. So this is secant to the 5th x dx minus secant to the 3rd x dx. And it turns out that this integral, by integration by parts, is what's called a reduction formula. And we could look it up, but I'm going to show you. Let's just do the secant cubed x, how you would do this if you didn't see it before and you didn't know the reduction formula. I'm going to go to the next page. I'm going to first do the integral of secant cubed x dx. And we are going to do this as integration by parts. To do that, I'm going to set u and dv, and then afterward I have du and v. I look at secant cubed and I realize the only thing that dv could be would be secant squared x dx, because that's something that I know the antiderivative of. So dv would be secant squared x dx, and u would be secant x. Du, the derivative of secant, is just secant x tangent x dx, but the antiderivative of secant squared is tangent x. Working this, we're going to go, it's this minus the product of this. We get that the integral of secant cubed x dx is, crossing this, it's secant x times tangent x minus the integral of secant x tangent squared x dx. At this point, I'm not sure what to do, so I am going to replace tangent squared with secant squared minus 1. Looking at this, look what I can write. I can say secant cubed x dx is secant x tangent x minus the integral of secant cubed x dx. But then I had minus a minus with the secant is plus the integral of secant x dx. But this can get added to the other side. In doing that, what we get is we've got 2 secant cubed x dx is secant x tangent x not minus, but plus the integral of secant x dx. And this integral, this last integral here, we have to memorize what that answer is. Continuing, we get 2 secant, the integral of secant cubed dx is just secant x tangent x plus the antiderivative that we've memorized of secant is the log of secant x plus tangent x plus a constant. And sure enough, the last step is we will divide by 2. Dividing by 2, we can put a half here. And we don't have to divide the constant by 2. It stays. Therefore, we get that the integral of secant cubed x dx is just secant x tangent x over 2. And this log over 2, or I write it as 1/2, the log of secant x plus tangent x plus a constant. And we could do the same with the integral of secant to the 5th. So going back here, this is the trickiest of all the cases. When in this particular case, when the odd one is the secant, we have to do by parts. And that's going to involve changing to secants, and odd powers of secant are what we call reduction formulas, which involve integration by parts. And when we're finished, we're not completely finished. We'd have to do the same thing for the integral of secant to the 5th.